So in this video we're going to find and interpret the basis of a one-dimensional subspace. So in this example we want to consider a subset of the vector space R3, and this is the vector that we want to consider, A twice A, opposite of A. Clearly it's a member of R3 because it's a three-component vector. So before we just jump into finding a basis and determining dimension, first we need to verify that it is actually a subspace, because when we look for a basis, we are looking for the basis of a subspace. So remember, to be a subspace of something that we already know is a vector space, all we need to do to demonstrate that it is a subspace is to show closure. Closure under scalar multiplication and closure under vector addition. So first we're going to show closure under scalar multiplication. So to do that, all we need to do is take a scalar C and multiply it by a vector of the correct form. So the vector B twice B opposite of B has the form A twice A opposite of A. And if I distribute the C now into the vector components, we get the vector CB comma twice CB comma opposite of CB, which does have the form A twice A opposite of A when A is equal to the real number C times B. So we're closed under scalar multiplication because we have the correct form when we multiply by a scalar. So now you need to show closure under vector addition. So to do that, we take two vectors of the correct form. So I'll take B twice B opposite of B, and then we add it to another vector of the correct form. So I'll use C twice C opposite of C. So now I have two vectors I'm adding together, both of which have the form A twice A opposite of A. We add them up, we get B plus C. We get twice B plus twice C. We get opposite of B minus C. And now I can rewrite this as B plus C twice B plus C, and factoring the minus out here, I get minus B plus C. And notice that this has the form A 2 times A opposite of A when A equals the real number B plus C. So when we add two vectors of the correct form, we get a vector of the correct form. So we know it's a subspace. It's a subspace because it was closed under scalar multiplication and vector addition. Once we have demonstrated it's a subspace, it is going to make sense then to look to find the basis of that subspace. And the way that we do this is fairly straightforward. We say, here's the vector A twice A opposite of A, and I'm just going to factor the A out of this vector, and I get a scalar times 1, 2, negative 1. And notice this means that the vector of the form that we have is a linear combination of this vector here. A scalar times this vector gives me every vector of the correct form. So you pick a value for A. I know what scalar to put here to generate the vector in the vector space. So this is a very straightforward one where we have the basis is just a single vector. So the basis for this vector space, this subspace, the basis for it is just the vector 1, 2, negative 1, because every vector of the form A twice A, negative A can be constructed from the vector 1, 2, negative 1 by multiplying 1, 2, negative 1 by the correct scalar. Because it has dimension 1, the geometric interpretation of this is it's going to be a line through the origin. Notice if I let A equal 0, I get 0 times this is the 0 vector. So I have a vector that starts at the origin. It points in whatever direction it points. And because I can scale it with any real number A I want, I can make it infinitely large. And I can use negative real numbers to reflect it through the origin in the other direction. So the geometric interpretation of this subspace is that it is all the vectors that lie on the line that contain the origin and and the direction vector 1, 2, negative 1.